Earth is not warm by accident. Every second, sunlight arrives from the sun, passes through the atmosphere, and heats the land, oceans, ice, and everything living on the surface. But if that were the whole story, Earth would lose heat back into space much more easily and the planet would be far colder. The greenhouse effect is the process that slows that heat loss. Certain gases in the atmosphere allow much of the sun's energy to enter, but absorb much of the heat that Earth later tries to send back out. This makes the surface warmer than it would be otherwise. It is not a rare side effect or a modern invention. It is a basic planetary process, and on Earth, it is one of the main reasons liquid water and life can exist at the surface. The key idea behind the greenhouse effect is energy balance. A planet warms when it receives more energy than it loses, and cools when it loses more energy than it receives. Earth gets most of its surface energy from the sun. The sun is extremely hot, with a surface temperature of about 5,500 degrees Celsius, so it emits energy mostly as shortwave radiation, including visible light and near-infrared radiation. This energy travels through space and reaches Earth. Some sunlight is reflected away by clouds, ice, deserts, and bright surfaces, but a large amount passes through the atmosphere and warms the surface. Once the surface has absorbed that energy, it cannot simply keep heating forever. It must release energy too. Earth releases energy in a different form than the sun sends it. Because Earth's surface is much cooler than the sun, it emits long-wave radiation, mainly in the mid-infrared and far-infrared part of the spectrum. This difference in wavelength is the heart of the greenhouse effect. The atmosphere is relatively transparent to much incoming short-wave sunlight, but it is much less transparent to outgoing long-wave infrared heat. A gas is called a greenhouse gas when it absorbs this long-wave radiation. Water vapor, carbon dioxide, methane, and other gases do this especially well. They intercept infrared energy that would otherwise escape more directly into space, reducing the rate at which Earth can cool. A common mistake is to imagine the atmosphere as a solid lid trapping heat underneath it. That is not quite right. Energy still escapes to space, and Earth still cools. The greenhouse effect works more like a delay system. Greenhouse gas molecules absorb infrared radiation, become energized, and then release energy again in different directions. Some of that energy continues upward and eventually escapes. Some is sent back downward, warming the lower atmosphere and surface. Across the whole planet, this constant absorption and re-emission changes where and how efficiently Earth loses heat. The result is a warmer surface than Earth would have if the atmosphere contained no heat-trapping gases. The numbers show how important this process is. Without the natural greenhouse effect, Earth's average surface temperature would be around -18 degrees Celsius. That is below freezing on a global scale. With the natural greenhouse effect, the 20th century average surface temperature was about 14 degrees Celsius. That difference of more than 30 degrees is enormous. It is the difference between a planet where ice would dominate much more of the surface and a planet with liquid oceans, rainfall, forests, agriculture, and stable human settlements. So the greenhouse effect itself is not the problem. A natural amount of it is essential. The problem is what happens when the effect becomes stronger than the climate system is adapted to. Earth's atmosphere does not absorb all radiation equally. In broad terms, it absorbs only a smaller share of incoming short-wave radiation from the sun, but absorbs most of the long-wave radiation emitted by the surface. This is why the surface can warm under sunlight, while its outgoing heat is slowed on the way back to space. Think of it as a selective filter rather than a blanket of uniform thickness. Visible. Sunlight can largely enter, but infrared heat is strongly affected by greenhouse gases. The atmosphere, clouds, and surface then exchange energy through radiation, air movement, evaporation, and condensation. Climate is the long-term result of all these exchanges, but the radiation difference between sunlight and Earth's heat is the central mechanism. Water vapor is one of the strongest natural greenhouse gases, but it behaves differently from carbon dioxide and methane. The amount of water vapor air can hold depends heavily on temperature. Warm air can hold more moisture, while cold air holds less. Carbon dioxide, by contrast, can remain in the atmosphere for a long time and can build up when humans burn fossil fuels. Methane is present in smaller amounts, but it is very effective at absorbing infrared radiation molecule for molecule. These gases are not identical, but they share a critical property: they interact with outgoing long-wave heat. By increasing their concentration, the atmosphere becomes better at slowing heat loss, and the surface must warm until a new energy balance is reached. The greenhouse effect is sometimes discussed as if it were a recent theory, but the basic science has deep roots. In 1824, Joseph Fourier proposed that Earth's atmosphere helps keep the planet warmer than it would otherwise be. Claude Pouillet later strengthened the argument with further evidence. In 1856, Eunice Newton Foote showed experimentally that air containing water vapor warmed more than dry air, and that carbon dioxide produced an even stronger warming effect. The term greenhouse was later applied to the phenomenon by Niels Gustav Ekholm in 1901. The details have become far more precise over time, but the foundation is old. Gases in the atmosphere influence how Earth gains, stores, and loses heat. Human activity changes the greenhouse effect by changing the composition of the atmosphere. Since the Industrial Revolution, societies have burned coal, oil, and natural gas on a massive scale. Burning these fuels releases carbon dioxide that was previously stored underground. Agriculture, energy production, waste, and other activities have also increased methane. These added gases do not create a new kind of physics, they intensify the same heat-trapping process that already exists naturally. With more greenhouse gases present, more outgoing infrared radiation is absorbed and re-emitted before escaping to space. That means Earth retains extra energy. Over time, this produces global warming, measured not by one hot day, but by a long-term rise in average temperature. By 2023, Earth had warmed by about 1.2 degrees Celsius since the Industrial Revolution. That number can sound small because local temperatures change by much more than that between day and night or from season to season. But a global average temperature change is different. It means the entire climate system has accumulated extra heat: oceans, land, atmosphere, and ice. Even a 1-degree global shift can affect rainfall patterns, heat waves, drought risk, snow and ice, sea level, and ecosystems. Since 1981, the global average surface temperature has increased at roughly 0.18 degrees Celsius per decade. That pace matters because societies, agriculture, coastlines, and infrastructure were built around a narrower range of past climate conditions. The greenhouse effect can also happen beyond Earth. Any planet or large body with an atmosphere can experience some version of heat retention if gases slow the loss of energy to space. The source of surface heating may be external, like sunlight from a host star, or internal, as with a giant planet such as Jupiter, which has significant internal heat. But Earth's case is especially important to us because the balance is delicate enough to shape oceans, weather, food systems, and habitability. The principle is simple: energy enters, energy leaves, and atmospheric gases influence the exit route. Change the gases, and the final temperature balance changes too. The most useful way to understand the greenhouse effect is not as good or bad by itself, but as a natural control on planetary temperature. Too little greenhouse warming, and Earth would be bitterly cold. Too much, and the climate shifts into conditions that stress ecosystems and human systems. Greenhouse gases matter because they determine how easily infrared heat escapes to space. The sun provides the incoming energy, Earth radiates energy back out, and the atmosphere regulates part of that exchange. That is why carbon dioxide and methane are so important in climate science. They are small parts of the air by volume, but powerful parts of the planet's heat balance. The greenhouse effect keeps Earth livable, changing it changes the world we live in. If you found this helpful, please like this video and subscribe for more explainers.